We're going to prove the part D and part E of theorem 1.9 today. So D says that a topological vector space is finite dimensional if and only if it is locally compact. And E says that if X is locally bounded and it has the high invariant property, then it is finite dimensional. So in some sense, D follows from E, right? E follows from D, right? So we will see this later. So let's first introduce some usual terminology we have. So in the Rn or Cn, which are the usual vector spaces that we have that are over R and C, we would denote a vector just by their components for each zk in the scalar field under the standard basis. EKs, so k from 1 to n. So EK are just the vector that is 0 almost everywhere, except the kth one is 1. So this will be the kth one. So this is just some usual terminology. And we have the norm on Cn. So a norm on Cn is also the usual one. We just square all the components and take a square root of it. And we also have other norms, other norms, like we have the one norm, with just the sum of the absolute value of every component. And we also have a sup norm, which is taking the maximum of all the components. So k from 1 to n. And we can actually prove that all these are equivalent. They actually induces different metric, but the topology, this right top as topology, they induce are the same. And we actually have a criterion for that, but we're not going to mention it here. And next, we say that a topological vector space, so a topological vector space X is dimension n if there exists a isomorphism onto Cn. And in this sense, this isomorphism will be linear and it's also a bijection, so 1, 1, on 2. And in this case, this topological vector space is said to be of dimension n. So actually, in some sense, there's only one vector space for each dimension n. Well, this is not completely true because these isomorphisms may not be natural. As one obvious example is that Cn is not naturally isomorphic to the dual of Cn. It's not natural. So upon a basis chosen, we can have an isomorphism. But this isomorphism depends on the basis you choose, so it's not always natural. But in some sense, we only have one if we always choose the basis. So we were going to prove that the results we mentioned above. Before doing that, we prove a little lemma. So lemma 1.20, which says that X be a topological vector space and F is a linear function from Cn to this topological vector space such that it is linear, then the conclusion is that F is continuous. This lemma will prove half of the theorem that we have below. So it's not hard to prove. So first part, we just choose the standard basis for Cn, standard basis of Cn. Then every z can be written as the sum of zk times ek. And by the linearity of F, we can actually write F of z as the sum of zk times F of ek. So now, this part is a constant. This is a vector that does not depend on zk. So it's a constant vector. In X, right? So if this part is continuous, then by scalar multiplication, which is continuous, zk times F of ek is also continuous. Then by the continuity of addition, this whole thing will be continuous. Now this function, zk, it's actually obvious that it's continuous in Z. So obviously continuous. So we have that by continuity of addition and scalar multiplication, F is continuous. So this is actually very easy to prove. So now we will prove one of the main results, 1.21, which corresponds to which one is this? Oh, not yet. Oh, okay. It's the next one. Let me check real quick. So it's this one and next one. So let's say stated later. So 1.21 says that n is an positive integer and y is subspace of X of dimension n, then A, for every isomorphism between C and Y is a homeomorphism. Furthermore, the subspace Y is closed. And combining this theorem, we can actually prove that it is finite dimensional if it is locally compact. So to prove part A, we first introduce some notation. So the ball B is just the usual unit ball, so z smaller than 1 in Cn, and we let the boundary of B be S, which is obviously a closed compact set that's inside Cm, right? Now what we do is we map this set S to X, which is, we map it into Y, which is inside X, and we call it K. And this is actually compact. It's compact by 1 to 1 of F. It is compact. So it's closed. So K is a closed set that does not contain 0. Then by the separation lemma we have before, it says V neighborhood of 0 in X, such that V does not intersect K. So you'll kind of have a image like this. You will have a set. This will be S, this is a boundary, the interior will be the ball, and you map it through F. And you can imagine that Y is this plane in X, so this whole plane is Y. And K will be a ring on this plane. And you will have a neighborhood here, which is in X, so it can be outside Y, so it looks something like this. And it lies inside K. Now, we map this back to, so this is X, this is Cn. We map V back to Cn through F inverse, and we call this E. So we will have a thing here. This will be called E. So E is the inverse image of V, which is the same as inverse image of V intersect Y. Now, because this image is disjoint from the boundary of the unit ball S, and as F inverse is 1 to 1 and linear, we can actually prove that by the fact that V is balanced. did I say that V is balanced? So we actually want this is balanced as well. E is also balanced. Therefore contains 0. Hence 0 is in E. These together implies that E lies inside double B, which implies that E is bounded. And we prove in the equivalence of a continuity that the D says that if a function, linear function, is is bounded in some neighborhood, then it is equivalent to that f is continuous. This is for functionals, right? This is theorem 1.18. So theorem 1.18. So to apply this, we simply look at each element of F inverse. As F inverse maps Y into Cn, we can just regard it as each scalar function at each component, right? Because we can have a standard basis in Cn. So we can apply 1.18. So this implies that F inverse is continuous. So combining the result of 1.20, so together with 1.20, F and F inverse are continuous bijection. Hence, F is a homomorphism. So this proves A. Now B, we want to prove that the closure of Y is inside Y, because the other direction is obvious. So this direction is true by definition. So what we do is we choose a arbitrary point in the closure of Y, and that the function f, the whole isomorphism, and the neighborhood as above. And we prove that this thing will cover the whole space eventually. So there exists T positive such that P lies inside TV. Then from the property of V from above, we actually have that Y intersect TV lies inside F of TB, which is obviously inside F of TB closure. So this part, the left-hand part, comes from the fact that F inverse of V lies inside B. So we proved this in part A. And because TB closure is compact, hence bounded. Hence closed. Of course it's bounded, but we need closeness here. Close. So we have that P lies inside F of T B bar, which is inside Y. And this proves that the closure of Y is inside Y. hence it is closed. So this finishes the proof of 1.21. And next we'll prove that every locally compact topological vector space is finite dimensional. So theorem 1.22, locally compact is equivalent to finite dimensional. So for X is a topological vector space. And the other direction is trivial, so we only prove other direction. So this direction is trivial. It just somehow follows from the Bogdanov-Weierstrass theorem, right? So we prove from the locally compact to finite dimension. So what we do is we choose a neighborhood that is compact after taking the closure, neighborhood V, where V closure is compact. Then by theorem 1.15, we prove that for any neighborhood, bounded neighborhood, so this implies that it's bounded and closed, as topological space is Hausdorff, so it is bounded and closed. So by theorem 1.15, 2 to the minus n times v is a local base. Next, we utilize the compactness of V bar, since it's compact. So it exists xi, I from 1 to m, such that V is contained in the union of I from 1 to n, xi plus V, half of V. Now, we denote the space that's spanned by these vectors, xk, k from 1 to m, by y. This is a subspace of X. And obviously, the dimension of this subspace is smaller than m. And by the previous theorem, by theorem 1.21, y is closed, because it is spanned by these vectors, which is the linear combination of this vector. So it is a space that can be regarded as an image of Cn, or Cm here, the integer here, Cm. So it is closed. So next, from this fact, we see that V is contained in Y plus 1/2 of V, together with the fact that any times of the subspace is itself, we can actually have the following inclusions. So first, 1/2 of V is contained in Y plus 1/4 of Y, which implies that V is inside Y plus half of V. Then we insert this here. We have Y plus 1/4 of V. Oh, did I say? I wrote it wrong. This is V, which is just Y plus 1/4 of V. Then we can continue this. So, we have that V is contained in Y plus 2 to the minus n times v for every natural number n. Then because 2 to the nv is a local base, so v contains inside all these. So n from 1 to infinity. This will actually be the closure of y, as we proven before, and this will actually just be y. So it means that y, which is spanned by these factors here, actually contains a neighborhood of 0, v. And again, by the theorem we proved before, we have that nv, if we multiply by n and union all of these, this will eventually cover whole of x, because every v lies inside y, so this actually is inside y. So this implies that y is the whole of x, which is finite dimensional. Is finite dimensional. So this finishes the proof. So this finish the property of a finite dimensional vector space, that it is finite dimensional if and only if it is locally compact. And next one will be a very useful property of proving some topological vector space having the Heisenberg property, or it is not locally bounded. We can do it either way. So let's do a remark here. So theorem 1.22 is D of theorem 1.9. So this is one for the main result. And next one, theorem 1.23 is E of theorem 1.9, which goes as follows. Let X be a topological vector space, such that it's locally bounded and it satisfies the Heisenberg property. Then X is finite dimensional. And it is very easy, right? So we only need to prove that it is locally compact. So locally bounded means that locally boundedness means that exists a neighborhood of 0 such that V is bounded. And together with the Heisenberg property, because V bounded implies that the closure of V is bounded. Therefore, V closure is a closed and bounded set. Now, by the Heisenberg property, V is therefore compact, which implies that Vx is locally compact. Then by the previous theorem, X is actually finite dimensional. So what we'll do in later sections is that we will prove some space we will prove is not locally bounded by this theorem, using the fact that 1, dim x is infinity. Dim x is infinity. 2, x satisfies the Heisenberg property. These together will imply that it cannot be locally bounded. Because if it is locally bounded, together with the Heisenberg property, it will imply that it is finite dimensional, right? So we have actually many important spaces that have this property. And we haven't proved that, but one of the important results is that if it is locally bounded, and together with, so that's actually right out. So it's theorem 1.9 C, which says that locally bounded plus locally convex and locally convex will imply that it is normable. So this is a C of theorem 1.9, which means that these spaces that possess the Heisenberg property with infinite dimensional will never be normable. They will have a metric as they will have a countable basis, but they will never be normable. So it's kind of harder to deal with. So they does not fit into the category of Banach spaces, but they do have a metric, so they have a nice topology, but it's just generally harder to deal with these spaces. And we will give 2 examples at the very end of this section. And next, we will talk about the metrization.